So let's look at a toy example here. So let's suppose we're given 5 observations with the following distance matrix. Okay, so I've given it in the form of a dist object in R. So the distance between observation 1 and observation 2 is 2. The distance between observation 2 and observation 3 is 9, etc. So the agglomerative methods all start with singleton clusters, the finest possible partition. So we've got 5 clusters, each one contains a single data point. Now then, how do the methods work? Well, let's think about single linkage first. Now, at the first stage, we join the pair of clusters which are closest. So if we look through these numbers here, we find the smallest distance is 2. That's the distance between observation 1 and observation 2. So we join cluster 1 and 2, okay, and that results in the clusters 1, 2, 3, 1, 2, and then 3, 4, 5. Now we have to work out the new distance matrix. Okay. So what is the distance between the cluster containing 1 and 2 and the cluster containing 3? Well, if we use single linkage, then we just take the minimum distance. So let's look at that. The distance between 1, 2, and 3. Well, the minimum distance is the distance between 2 and 3, and that's 9. Okay. So if we put this distance matrix together, the distance between the cluster 1, 2, and 3 is now 9. Let's think about the distance between 1, 2, and 4. So 1, 2, and 4. Well, again, we take the minimum of these two numbers. So it's 13. Okay. So the distance between 1, 2, and 4 is 13. Finally, let's do the distance between 1, 2, and 5. Well, that's the minimum of these two numbers using single linkage, which is 5. So we get 5 here. Now, the other clusters haven't changed, so these numbers are the same as before. Okay, so that's stage 1. At stage 2, do the same thing. We find the minimum number here, so that's the distance between 3 and 5, which is 4. So we join them together. So now we get the clusters 1, 2, 3, 5, and 4. And again, we have to think about what the new distance matrix is. So the distance matrix between 1, 2, and 3, 5 is the minimum distance between these points. So that's a minimum of 9 and 5, so it's 5. So the distance between 1, 2, and 3, 5 is 5. The distance between 3, 5 and the point 4 is just the minimum value of that. So that's the minimum of 8 and 10. So we get a distance of 8. Okay, so it gives us this new distance matrix. Now the next stage is to say, well, what's the minimum here? And join those two. So the minimum here is 5. So we join together the clusters 1, 2, 3, 5. So that gives us a new cluster 1, 2, 3, 5, and 4. At the final stage, we just join them all together to get a single cluster. So that's how these methods work. So that's with single linkage. Thankfully, you'll be pleased to know there's an R command to do this. So it's this hclust command for hierarchical clustering. And all we have to do is specify the method. So to do the single linkage method, like we just did here, I put method equals single. It gives us an object back. Now, the best way to think about these is either to use the cut tree command or to look at a dendrogram. So what a dendrogram does is shows the ordering of the clusters and the height at which they were clustered. Okay, so if I do plot of the object I just found, I get my dendrogram. So remember, what we had in the method was that 1 and 2 were joined first, and the distance between 1 and 2 was 2. Okay, so we got 2 here, that's the height at which they were joined, and they were joined first. So if we go up the tree, we find the next 2 to join with 3 and 5. And remember, they were joined in stage 2. The distance between them was 4. So if we look back at our dendrogram, you can see they were joined at height 4. They joined next. We keep going up. We find the next join is between the clusters 1, 2, and clusters 3, 5. So that happens here. And that was at height 5, which is what we found. And then finally, we go all the way up, and we get them all joined together at height 8. Okay, so that's a dendrogram, and that's a useful way of visualizing these clusters. To extract the clusters, we can use this cut tree command. And what we have to specify then is either the height at which we cut or the number of clusters we want. So to specify the number of clusters, we specify k equals 2, say, and it gives us a labeling for each of the points. So there's 5 data points here, remember. It tells us that point 1 is in cluster 1, point 2 is in cluster 1, point 3 is in cluster 1, point 4 is in cluster 2, and point 5 is in cluster 1. Okay, so that's what we found in this final stage here with 2 clusters. Yeah, we got 2 clusters, 1, 2, 3, 5, and another cluster just containing 4. Okay, so that's what this cut tree command has given us here. The other way to do it is to specify the height at which to cut. So if we want to cut the tree at height 4.5, say, so that'll be a line somewhere here. Okay. You can see that we're going to get out 3 clusters here. We're going to get 4 in a cluster, 1 and 2 in a cluster, and 3 and 5 in a cluster. So let's look at the output from that. That's what we get. Yeah. So point 1 is in cluster 1, point 2 is in cluster 1. Point 3 is in cluster 2, and point 5 is in cluster 2. Point 4 is in cluster 3. Okay, so this is another way to cut the tree and find clusters, either by height, which is specified by this h equals something, or by the number of clusters, this k equals something. But what's underlying it all is the dendrogram, and that's the way to think about hierarchical clustering methods, as a dendrogram. Okay. So this was with single linkage. Now we've talked about 3 different linkage methods, so let's have a look at a different method. So let's look at complete linkage. Now it's a bit harder to think about complete linkage, and average linkage is harder, but let's have a think about how they work. So at stage 0 again, we still have 5 clusters, singleton clusters. Now, stage 1 is just going to be the same. Stage 1 works with the underlying distance matrix. So we just find the minimum distance between points. So again, they're all going to do the same thing at stage 1. They're going to join cluster 1, cluster 2, because that's the smallest distance. So all the methods are going to join these 2 together first. But what changes now is the distance matrix that we get left with. We have to compute the distance between the clusters we started with and the new cluster. So if we go back to our original distance matrix here, we've joined 1 and 2 together. So what's the distance from 1, 2 to 3? Well, with complete linkage, it's a maximum distance. So these are the 2 distances from 1, 2 to 3. So we're going to get a distance 11. The distance to 4 is going to be the distance between 1, 2, and 4. It's going to be the maximum of those distances. So it's going to be 15. The distance between 1, 2, and 5 is going to be 7. If we go down, look, we get this new distance matrix. So what do we do at this stage? Well, again, we join together the clusters that have the smallest distance, which is going to be the clusters 3 and 5. We're going to join them together, so we're going to get 1, 2, 3, 5, and 4. And now, when we think about the distance matrix, what's the distance between 1, 2, 3, 5? Well, it's the maximum of this number and this number. Okay, so it's going to be 11. Okay. So we're using the complete linkage method. We pick the maximum distance. What's the distance between 3, 5, and 4? Well, it's the maximum of 10 and 8. So it's going to be 10. Okay. And the distance between 1, 2, and 4 doesn't change, it's still 15. So at the next stage, we join the clusters that are closest. So that is clusters 3, 5, and 4. That's 10. So that's different to what we did last time. So now we get the clusters 1, 2, and 3, 4, 5. And then at the final stage, again, we just join them all together. Okay, so if we plot this, well, just note that to do this in R, we use this hclust command, and we use this. We just specify the method to be complete linkage. If we do that, we get a different dendrogram to what we found previously. 1, 2 join first, then 3, 5, then 4 joins 3, 5, then they all join together. And finally, we could go through the same thing with group average, but I'll just give you the result instead. And all we have to do here is specify method equals average. Okay, if we do that, we get a tree that looks a lot like the single linkage tree, okay, but note that the heights have changed here. So we are getting a different result. Okay. So how do we choose between methods? Well, there isn't a single answer to this. The methods have various different strengths and weaknesses. Okay. In the case where the data are really split into distinct, compact clusters, and compact in the sense that all the observations from the cluster are relatively close to each other compared to the distance to other clusters, then all the methods are going to produce very similar results. It doesn't matter. When it does matter is when the clustering is less obvious. Now, single linkage or nearest neighbour linkage tends to work. You've got two clusters G and H. If there's a single pair of observations that are close, they get joined together. Okay. So therefore, with single linkage, we can sometimes get a chaining event. So you get points that can end up very far apart in the same cluster just because there's a path between them of closely related points. So as a consequence, we can end up with these clusters that are not very compact. So sometimes one of the quantities people look at in cluster analysis is sometimes called the diameter of the clusters. So if we look at the maximum value of Dij for all the points I and j within that cluster, that gives us the diameter of the cluster. So single linkage methods can produce clusters that have very large diameters that can be very spread out. Complete linkage is the other extreme. It only joins two clusters if the furthest pair of points are close. So this tends to produce clusters that have very small diameters. But the downside of this is that observations assigned to a cluster can sometimes be much closer to members of other clusters than they are to members of their own cluster. Okay, so it's not a perfect method either. Group averaging, in some sense, is an intermediate point between this nearest neighbour clustering, a single linkage, and the furthest member clustering, complete linkage. Okay. It tries to take the average distance between the two clusters. But the problem with group averaging is that the method isn't invariant to transformation of the distances. And so, the point I'm trying to make is that there's no perfect method here. Arguing between the methods, there's lots of arguments in favour of each method, and it comes down to a subjective opinion in each case about given what we know about the problem. And really that summarises clustering methods overall. There are many different methods for doing clustering, but there's not a single best method. And the algorithms don't produce the same answer. And even sometimes the same algorithm with a different initialization will produce different answers each time you run it, like k-means will, or model-based clustering will. Okay. So there is a fairly large kind of subjective element when assessing each method. There isn't an answer. There are many answers, and you have to argue for why your answer makes sense and why you believe your answer, and why it's a useful answer. So despite all these kind of caveats and warnings about clustering, it's something that can be useful in practice, but you're not going to necessarily reveal some great underlying truth. It's used as an exploratory tool to suggest to you things you might look at in more detail.